Okay. First of all, thank you to be here for the lecture of today. We will start now officially. And last time, as I told you before, we have seen in a mechanical system. Therefore, I introduced the concept of the friction. We have seen also a relative advanced friction model. You remember this Coulomb? And yeah, today, today I will go ahead with the chapter dedicated to the modeling, considering an electrical system. As I told you before, typically in robotics, in automation, the systems to be controlled, to be modeled, and then to be controlled are system which is mixed between electrical, mechanical, hydraulic, and I hope that I can show you and then at least very quickly a system which consists of an electrical mechanical part is not so difficult to image. For instance, in a motor. And a motor, an electrical motor means electrical part, of course, but of course, as in a motor, the model involves the mechanical, dynamical system, dynamical equations, no? Because of the movement. But we will see in detail. Now, let me go ahead with this. In order to, let me say, to complete, I don't want to say because modeling is a real very large topic. Yeah, there are courses. You didn't receive the material. Let me check the email. Let me check the email. I think you should wait a little bit because uh, it seems to be that I sent the material to your address. Let me see if I receive some notification. Probably you need a little bit time because here it seems to be, or let me see again. Let me check again. Um, Let me resend. Let me resend. One second. Let me resend because it could be that you're right, that you have some problem with the email. Mhm. Uh, Let me resend. Brr, second. Oh, where is now? Hmm. Oh, second. This email is always the problem. It could be that you didn't receive the email. Uh, Also, my email in the morning, which I tried to communicate, that the lecture of today will start a little bit later. It could be, but I see problem with the email here. Okay, let me restart again. Let me resend again. But I see very lecture of today's lecture of today. Let me try it again to send you. Okay, it seems to be sent. Yeah, now it seems to be sent. It is possible that today in the morning you didn't receive my email with the content. Please wait for me because I will start a little bit later. Mm,
We
some
received
problems
that
with
mail.
the email, but now it seems to be that you received. I hope. Okay, let me now. Uh, let me see the chat. If you want, I can put in the chat because I see some problems today with the email. Let me see how I can do that in the chat. Yeah, also to upload here. Let me see if I'm able to upload. Uh, mm, lecture. Now I have to look for the name. Excuse me, but really when the mail does not work, there are problems. It's now. Found it. Okay, now you have in the chat. Now in the chat. I will check the mail. Okay, now the material are on Outlook. Oh, perfect, perfect. Now we have it twice in the chat and in the Outlook. Okay, let me start again. And as I told you, the idea in this, the chapter of the modeling is to show you this electrical part, and we have a scene in an electrical system. Then at the end, we have a scene in a mechanical system. Last time, mechanical in the sense mechanical means for us that we describe the system using equation of the dynamics, no? Newton law. Do you remember I told you a lot? And I try also to investigate some let me say mechanical aspect, no? The friction. Do you remember the Coulomb friction, no? For instance, the friction in the linear sense, and then I advance a little bit this. Today we will see the system here. So we have an overview on the two most important model strategies, mechanical and electrical, and then I will show you quickly also how we can consider system which are, let me say, which have both, you know, electromechanical system. Of course, in robotics, in actuators, in technical system, typically we have a combination of these two systems, or not only these two. Do you remember I told you hydraulic, pneumatic? I don't have time to tell you everything because the course consists of control basically, but control needs model because we will see when we consider model predictive control, when we will consider sliding mode control, some control strategies are model based. During the semester, we will see also another kind of system, not only this technical, which is used in robotics, which is used in, let me say, in technical process, but also model related to different system. As I told you, we will see also the model related to the epidemiology. Okay, look at the system here. Yeah, let me start. Is an RLC circuit with this particular configuration. Probably is known something similar from electrotechnic, and which I don't know if you remember, we have seen a series between LRC. We have seen also parallel between RLC. Do you remember this resonance or resonant circuits? Therefore, I am considering a variation because probably after this lecture, you can apply our knowledge, consisting of state variable, consisted of this particular representation through matrix A, B, C, D, also in a different configuration, which you already know. Therefore, this particular topology, no, it's not order topology. Not only didactically, this system here is a system which can be seen also in some, or at least, let me say in some applications. I would like to show you a particular application which is modeled, yeah, this is the problem of the modeling, exactly with this topology. Let me show you quickly 2 slides before analysis analytically, before building the mathematical model. Let me see if I find quickly this presentation. Let me see where I can find this. I can find this. In order to justify a little bit better this particular topology. I consider this not only again to propose a variation of this classical resonant circuit, but let me see if I find. Um, yeah, probably. Now, just a few slides. Probably here. Yeah, found it. Now I share. Let me share in order to justify a little bit better. Let me share. Look at this lecture here. I don't need to send this lecture because this is the lecture is related to another course, the course of Kalman filter. But I would like just to show you 2 or 3 slides in order to motivate you, to motivate you in the sense to stimulate, I would like to say, to put really in focus the model or the modeling. Desiccator system using radio frequency. We have here the range, which in particular we are working on. It's a real project. No? It's already almost closed. We can see also this presentation. The origin, we started with this presentation. I mean, I produced this presentation when we started with the project. No? Radio frequency, using radio frequency generation. Look at this picture here. Yes, it's not so nice to see, um, but we can see a room and a humid room. Now I clarify why. The word desiccator can somehow justify probably uh, let me say this humid room. We have two elements here. We can see a high frequency generator. Believe me, even though it's not clear what this is. And then here in close, we have a matchbox adapter, an adapter. In general, in this room, we can see from this picture that try to image that we have two electrodes. We have basically in a big, or we have different equipment, but try to think in a big capacitor, realized between two electrodes, as always, one we call warm, and other one cold electrode. Here, this adapter, this matchbox is there to match what? To match the high frequency generator with this capacitor or capacitors, because could be also more than one. In order to understand better what I want to show you, and I will conclude with this slide. Now, look at the button. We have the electrical network with our inputs, the electrical network from which we have at home. Then we have a system which is the radio frequency generator. I don't need to go in depth on this radio frequency generator. I don't need to go in depth with this matchbox, even though the matchbox I told you is something which adapt the impedance, the output impedance of the RF generator with the input impedance of our system, which consists of capacitors, in this case here, in this particular, could be also just one, depends what we want to desiccate. Yeah, but probably you know better than me, this adapter, impedance adapter is not the topic of today. Also, the RF generator is not the topic of today. The topic of today is exactly, look on this corner of the presentation. We can see exactly what I would like to present today, an RLC circuit in this particular topology or configuration, which can present, look at the system here, can represent exactly the desiccator system, or better to say, this part of the desiccator system, which at this moment, not only this part, no, also the matchbox, we can see in fact is an inductance which reflects or try to model the inductivity behavior or component of the matchbox. And the U1, basically U1 is the signal which is come out for RF generator. Basically, this RLC circuit can represent schematically in the first approximation the whole system which I would like which I presented, let me say, even though quickly. Few words about these capacitors. We can see here is as if we have let me see which configuration I had, because I am not able to see with my glasses. Yeah, we can see here that it's as if in this configuration, as if we have many capacitors connected in parallel. No? We can see that this conductor here and this conductor here, they are common. with parallel series, I would like to say. No, let me see exactly, because I don't see, yeah, something, something like that. I don't see very well with my glasses now. But anyway, we have an equivalent in any case, an equivalent capacitor which uh, can be seen here in in uh, in this configuration. Let me see again 1 second. Yeah, they are parallel. It seems to be they are parallel. To conclude, this system here, which is relatively complex, and the first approximation can be modeled with this LRC in this particular configuration. Believe me, we did exactly so at the beginning, then we did some modification, but basically this is the model. Or with this model, we can really control, we can really monitor at the beginning the temperature, which we need to desiccate. Desiccate, probably you know what I intend. No? Here in the middle, you can put some products. Here is uh, it's dedicated, exactly this structure here is dedicated to the desiccation of tobacco, for cigarettes, for instance. Sometimes, if you have a very, very uh, large, I mean, in this case, when you have just one big capacitor, sometimes it's used to desiccate um, uh, large elements with a large surface. It doesn't matter what, for instance, um, paint, paint. In the restoration of paint, if you have to eliminate the humidity, this isn't a big problem. This means should be controlled the temperature of inside of this capacitor using this signal U1, which we indicated in U1. It must be controlled in terms of amplitude and in terms of frequency. Remember, at the beginning, I know this is the range. But anyway, independent of this technical aspect, now coming back to our lecture, we have we are more aware about this model here, where it can be used, for instance, but not only in this application, equations to control or to monitor the temperature, which is not included in the model. Please pay attention. The temperature is not included in the model. In another advanced model, we included the temperature. The temperature makes a big difference because we can control probably more directly, not probably really more directly, but the model is more complicated. We end up in a nonlinear model. Very easy, we end up in a linear model. And do you remember last time I told you that the friction, the Coulomb friction, if I introduce the Coulomb friction, we have a model which is nonlinear. This means sometimes nonlinear is not so easy to be controlled. Nevertheless, with this system here can be controlled, yes, because we have a relative direct relation between voltage on the capacitor, this is U2, and the temperature, which we'll establish inside. Okay, let me look at the first equation. The first equation is this one here. Probably you know better than me, the Kirchhoff balance. U1 equals the voltage which we have on the inductance, UL, which is L multiplied the derivative of I1 with respect to the T, plus U2, the voltage on the capacitor. This came from this clean. Look what I am doing now. Instead of in this form here, I will put in this form. Easy. It's just to, let me say, reformulate. I don't want to say change a little bit let me say, to realize an explicit expression of the derivative of I1, the current we can see here on the inductance, equals the derivative of the current of inductance with respect to the time equals all the rest, but based on this equation here. First state equation. Do you remember about the state I told you last time? The state or the states or the state variables are variables which reflect the energy of the system. Why I1 is in a state? Because in this system here, we have two independent energy, the electromagnetic energy and the electrostatic energy. The electromagnetic energy is related to the current. It could be that I have something to tell you a little bit later. This means the variation of the current is basically the variation of the energy. The variation of the current reflects the variation of the energy. Do you remember last time? We have position and velocity. Here we have current in the coil and voltage in U2. The current, the variation of the current I1, the current, the voltage, is equals something as a function of the input, of course, as a function of the state. Now, basically, the energy, the electromagnetic energy, is a function of what I am doing in input and what I have as energy in the system. Of course, it could depends also from the current. At this moment, in this equation now. Second equation. The second equation is extremely easy, if you think. Because it's related to the second state. As I told you, the second state is U2, the voltage on the capacitance. And if you remember the definition of the capacitance or the capacitor, we have this equation here. The equation states that the current on the capacitor is equal to C times the derivative of U2, excuse me, U2 with respect to the time. U2 is the state. This means, in accordance, you remember last time I told you the structure of a linear system, which is basically, which consists of the X state, as I told you in this case, I1 and U2, the energy which we have in the system, the independent energy which we have in the system. Why I'm using independent? The reason, you remember, I told you before when I told you that the capacitors are connected in parallel. We don't need to put many voltage and a voltage for each capacitance, because they are characterized by the same voltage if they are parallel. That is the meaning of independence. X derivative, the derivative of the states, equals the variation of the energy, basically, is the function of the energy itself, plus the function what I am doing in input. Basically, the energy, the variation of the energy depends on the energy itself, the level of the energy itself. And of course, you can see the variation of the energy depends on the energy itself, plus what I am doing with the input, the energy which I am putting in the system. But about that, I told you a lot of last time. Let me now concretely, as last time, tell you about the energy quickly, because it's quite similar as last time. We have two kinds of energies, independent energies. Energy in the capacitance, energy in the inductance. This is the energy in the capacitance. This is the energy in the inductance, or inductor, if you want, or capacitor, if you want. I don't know if you remember these two equations. If you don't remember, I have here quickly the demonstration. Assuming that, you know that the energy is I told you also last time that therefore I am trying to do quickly, is always defined as the integral of the power. Let's consider just the capacitors. But the power is the product in this case. Last time was different because we had a dynamical system in terms of a mechanical system. Here we have the integral of the voltage on the capacitance multiply its current. But in accordance with, as I told you before, about the characteristic of the capacitance, I can write that IC, the current of the capacitance, or the capacitor, I can write in this formula. And I don't know if you remember the integral of a function multiply its derivative is this one. 1 divided 2, c is a constant, u2 square, no? The function square. Minus, you remember here, the initial condition, the energy at the beginning. You remember last time we have seen in the case of velocity and position, yeah, is the case of the capacitance. Of course, if the capacitance at not lowered, if you see at time 0 when I start with the simulation, when I start to observe, when I start to monitor, when I start to control, this is 0. If I do the same consideration for the coil, the inductance of the inductor, I can do basically the same. Of course, here we have, instead of UC, we have UL. Instead of IC, we have I1, because it's related to the energy of the coil. Again, if you remember that UL is L multiply di1 with respect to the time, I can do similar consideration. I can do similar calculations. 1 second. We say that the calculations are dual because this is enough to replace C with L and the U2 with I1. And you look, we have the same expression. Of course, here, assuming that if I1 square at time 0 is 0, this is not there. But basically, the calculations are the same, formal is the same, in one case with the capacitance, in one case with the inductance. This just to justify mathematically these two expressions and why U2 and I1, or I1 and U2, represent the state variable, because they are directly, let me say, connected, roughly speaking, with the energy of these two elements. Look at these central equations here. Now, as I told you, as I clarified, we have the first equation. We have the second equation just considering the definition of the capacitance. But the idea is to put the equation in this form here. The derivative of the states equals, or they are the function of states and inputs, in order to obtain exactly this representation, which I told you x dot equal a multiply x plus b multiply u. Now, the problem which we have here, nevertheless, is that IC is not a state. U2 is a state. U1 is an input. You remember the goal is, last time I clarified a lot, to obtain this kind of structure. The derivative of the states is a function of the state and the input. We don't have different elements. This means here, in this representation here, IC disturbs us, because IC is not an input. IC is not a state, but it's easy to replace, because if you remember that IC, if you look at the topology of the circuit, let me come back. What is IC? IC is this one. IC is I1 minus IR. Node balance. Remember Kirchhoff. IC is equal I1 minus IR. Clear? IC equal I1 minus IR. But IR is U2 divided R. IR, the current on the resistance, is U2 divided R. Clear? Then, if I replace IC with this expression, I have this expression here, which now we obtain our goal. The derivative, or the variations, let me say, of the energy, which is reflected by the variation of the states. These variations are function of inputs, one input in this case we have, and states, I1 and U2. We don't have other element, just input and states. This means our goal to represent the variation of energy as a function of energy itself and the input is achieved. Yeah, I repeat it for you again, this expression, which is our model. We have the mathematical model, of course. When I try to explain mathematical model, when I say mathematical model, why I emphasize this? Because also this is a model. Because we have a real system, which I try to present quickly, no? This desiccator system. Real system with coil, with windings, with these electrodes, with these two plates, and so on. The resistance represent the element to be desiccated. Cigarettes, tobacco, or a paint, the resistance. Here's this match, this adapter. Here is basically these two electrodes which I need to increase the temperature of this resistance, which our element to be desiccated. This is also in a model, this in a graphical model. But in order to control, in order to work with our computer, we need the mathematical model. But of course, we need a mathematical model in a particular form. You remember also last time, from this language here, this is more mathematical language, differential equation in formal structure, we try to transfer this information here, this format here, is in a matrix vector form. You remember, we have seen. We have seen. Now, what happens is we do the same exercise in which we have the derivative of our states in the vector equals in a matrix, multiply the state vector plus the vector, in our case, the vector, could be also a matrix if you have more than one input, multiply the input or the inputs, which we can see the matrix A, the matrix B, X is the matrix of the states, X derivatives, the derivative of the state vector. Basically, in each component of X dot, we have the derivative of the state, excuse me, yeah. Yeah, do you remember last time? Row multiply column plus this, multiply this. I will get completely this information here because this is equal to the first component of what happens, what we have excuse me, what we have in the right part. The same for the second line, let me say line. The derivative of u2 with respect to the time is row multiply column plus 0 multiply this one. And we will obtain this. We can see very well. This multiply this, minus this multiply this, plus 0 multiply this is exactly this. We have seen last time more in detail. No, again, the derivative of I1 with respect to the time is row multiply column plus 1 divided L multiply U1. 0 multiply this minus 1 divided L multiply U2 plus 1 divided L multiply U1. Look, is exactly this. Because here we don't have I1, and 0 multiply I1 allows to say that this representation reflects exactly this. Output matrix. Do you remember the output matrix? The output equation, if you want, in general, states what I want to observe. This means what I want to control. But anyway, the output we select it because we want to have a focus. No, we want to consider, for instance, here the U2 is exactly the case of the desiccator because the voltage of the capacitor reflects the temperature or is connected with the temperature. Y of t is U2, and the matrix C, Cm sometimes, because C here in this case is related to the capacitance. 0, 1, which multiply the state x, the state x is the same. 1 is fixed state vector, in our case, remain in the dynamics equation as in the output equation. Here, I put the output matrix because we have just one matrix which characterize the output equation. 0, 1, very, very easy. We have seen last time many more in depth, probably, no, if you remember. Look at this now, this sentence here. If I want to control or to observe, to monitor, not necessarily we need a control, but probably. Because of course the temperature is could be dangerous, no? Could be dangerous for the object to be desiccated. We have also possible strategies, possible profile of the temperature to be followed. And this means we need a control. If I want to control, for instance, UL for different reasons, not exactly our first task, assuming that. And just to do an exercise, because in the exam, in the project, it could be I ask to write the output equation for different outputs, the voltage of inductance. It could be also to protect, for instance, the inductance, to protect this adapter. Anyway, it doesn't matter which task we have. In this case, with this task, UL is our output, if this is requested, which is L multiplied di1 with respect to the time. L, which multiply this equation here. Why that? Because the derivative I1, excuse me, with respect to the time is already known, is something structural, which came from the system. We cannot neglect this structural equation. The model represents how the system works. The model represents how the system works, or at least ideally, or at least with some hypothesis. Anyway, if I plug in here the equation of the model, it's easy to see that at the end I have that UL is U1 minus U2 if you do these calculations. Look. Now, to conclude this part, I can put everything in matrix CM, as in this case is 0 minus 1, not 0, 1 as before, because before we had just U2. We have a minus U2. But here, very important, we have a U1. This means the matrix D, this time is not 0, but 1. Basically, at the end, I want to obtain a representation, as last time, consisting of 4 matrices, A, B, C, M, in this case, D, the dynamical equation, and the output equation. Nevertheless, both equations are characterized by X and U1 as element which characterize the variation of the states, but also the output. Now, remember, I insisted last time a lot of this representation, which holds basically just for linear system. If I have a component non-linear, we have to use different representation. Basically, we don't use matrices, we use directly the fields. I will tell you a little bit later when we will consider the sliding mode control. 1 second. I think what I sent now is already here. But before sending you other material, let me show you this. You don't need now, I don't need to send you, because this is extremely easy to understand and possible. If I ever will send you later. Now, I tell you this, we take a rest a little bit, and then we will restart with other material on this example here. No? We remain on this example a little bit. Here, I tried at the end, it is the time, to try to draw an analogy between this mechanical system of last time, the electrical system of this time. You remember? Here, I didn't consider the whole systems. I consider just a part of them, but if you want, you can do at home the rest. Is not exactly It's not exactly, in particular, this the system which I am considering here. Basically, we have just an RL circuit. Basically, as if the capacitor is not connected. Because the idea is to compare with this system here, which is not exactly yeah, the bow system is mechanical last time and electrical this time, and not directly comparable. But if you don't consider here the capacitance, yeah, just an abstract. In fact, here it's not written that this big example. Last time I made mistakes before. We have a mechanical system, we have an electrical one. They looks like, yeah, as our, but we don't have the here the capacitance. Anyway, we can see a little bit the analogy, just to show you that the velocity becomes the current, mass becomes an L. But probably you know that from electrotechnics a little bit, from physics. Here, the input, which is a force, becomes the voltage. Yeah, here, Kf, the friction becomes a resistance. We can say something more in general. No? This is a general analogy. It's not exactly our systems, in particular the electrical one, is not exactly the same. But we can see that nevertheless, the concept of the states, we have an electrical states, here we have a mechanical state. They, if I change here nominally the letter, we have exactly the same equation, but of course I have to change also instead of mass L or that instead of L mass, depend what I want to compare. And this is also interesting. This is also interesting because V is the energetic energy in the mechanical system. The current is, as I told you, the electromagnetic energy. Here is more interesting because we have two elements. In both cases, they represent the inertia of the system. I don't know if you remember. M is easy to remember. That's the inertia, the mechanical inertia. L, if you remember electrotechnic, is the electrical inertia with respect to the current. L try to limit, let me say, the variation of the current, as M try to limit the variation of velocity. Here is quite similar. We don't need to spend much word in the input. In one case, the voltage, in one case, the force. Very interesting, this one. This analogy or this parallelism are represent, you remember, in electrotechnic, the losses in the electrical system. Kf, I told you a lot last time, with different form, but in any case, Kf represents the losses of a mechanical system. Okay, I think we can take 50 minutes for a coffee. At least I need that. If I have, I will send you this, but I think this is, probably from your pre-knowledge. Again, it's not exactly the perfect comparison. We can do that also, but of course, we can do, but it's not exactly this what the intention on this slide here. But in general, we can see that we have a losses in electrical system, as in mechanical system. We have states in accordance with the energy in electrical and mechanical one. Input is trivial to say, but also, excuse me, losses, and also inertia. Again, I may make a little bit mistake. This is the losses, electrical and mechanical. Here's inertia, electrical and mechanical. Okay, let me take a coffee. Then we will come back with some. Let me see what I have. Some issue on this system, the desiccator, let me say. Then probably I will show you just the model of the motor, which is a combination of electromechanical system. And then we will start with some concept of control, no? Because at this moment, we are able a bit
Can I
to
have one more
understand and to build
question?
the model. Also, we have seen also this parallelism, let me say so. And with the model, we can really start working on control because, as I told you here, already we were able to characterize outputs. This could be also interesting to control UL, even though, as I told you, for us, the first goal is to control U2. No? Let me show you what I've done again. This here. Through the model is more characterized, of course, by the dynamical system or the equations, because the dynamical equations don't change. The dynamical equations don't change. The output depends what I want to control or to monitor. Of course, I can control and monitor both. No? If I want to control both, of course, we have a matrix CM, which is, please pay attention, 0, 1 first line, 0, -1 second line, because why, if you want, I can write here, and then we take a rest. If I if I need no, to control or to monitor. No? Control is stronger than monitor. Monitor means I don't do anything. I just observe what happens. And eventually I can shut down the system, no? Of course. Otherwise, why am I monitoring? Control is something more. No? Or monitor. Y equals U2 of t, UL of t, comma, then of course, the control or the control system is more complicated. Then, let me write for you. The dynamical system a dynamic equation of course remains same. Why that? Because the dynamic equation characterizes the behavior of the system. This means x derivative vector equal a multiply x of t plus b multiply u1 of t with a matrix A and B, which remain the same. Which remain the same, comma, but y of t equals u2 of t, ul of t. I mean, A and B remain always the same, independently what I am choosing as an output to be controlled. Now the matrix C I1, no? The first is I1. No? The first state is I1. The second is U2. Let me consider this and then at the end the matrix B. Again, here X remain the same. U1 in this case remain the same, the input. Y 0, 1, 0, -1, because it's the combination of what I have seen before. Huh? U2 was characterized by the matrix 0, 1. And here, do you remember we had 0? I can show you now. And if I want to observe or to monitor UL, UL was minus U2 plus U1. This is our new B matrix with two elements. And here is the new CM matrix with four elements, or 2 times 2. Why that? Because I have to combine this information here, 0, first component of the matrix B, first row of the matrix C, 0, 1, first component 0, first row 0, 1, and then I have to consider this information here as the second output if I put here as the second output UL. Typically, formally, we have a maximal priority and so on, but you can put as you want, of course. If you invert, here we have instead of 0, 1, we have a 0 minus 1. Instead of 0 minus 1, we have 0, 1 if you invert the order. And here also 1 instead of 0 and 0 instead of 1. This, to control this is more difficult, of course. We don't have time in this course to attack the problem multi control systems or multi outputs in a sense, but it's possible. No? Why is this more difficult? Because you have just one input. This means we have to fix the priority. Priority is to control U2 because we don't want that our product will burn. No? And the desiccator, when desiccation is difficult, what happens is that what we want to control, the temperature, burn out. No? We don't want. And also, second priority is to control the voltage on the inductance. But of course, they are connected. U2 and UL, they are connected. Why are they connected? Look at the equation. Equations, if you want. We don't have 0 here. We can see that. This means, oh, in any case, also thanks to this element here, U2 influences the current or the variation. This means the current U2, directly the variation of the current U2, I1, excuse. U2 influences the direct derivative of the current. This means indirectly the current, but the current influences UL. That we have seen here. No? UL is a function of the derivative of the I1. But I1 depends on U2. The system is totally connected. Also here, no? As I told you at the beginning. This is not 0. This is not 0. I mean, excuse me, to be precise, this is not 0. Right? Oh, yeah, this is not 0. This is not 0. This means they are connected from both sides. If this is 0, we don't have the connection between U2 and UL. This reflects UL. If this is 0, we don't have the connected connection between I1 and U2. They basically then they influences each other in both directions. This means they are connected. To control with one input two variables which are connected, you can understand that we have to be careful, no, in this sense. But of course, putting priorities, we can try to find a compromise. Of course, with the goal that U2 must be controlled such that at least my product does not burn out, and then of course taking care that UL does not exceed some values. Okay. I think we can take a rest now a little bit. Now it's a small 3 o'clock. 15 past, we will come back here. Let me see if I am able to put a pause. Let me see. In this news, Zoom, I don't understand how I can. iPhone here. No. Let me see. I don't find the way to. Should be here. Why then? Ah, now. Now, okay. We will see in 15 minutes, 15 past 3 o'clock. Let me uh, put a pause in the recording system. I found it. Yes. You can see here now another possible configuration of outputs. We can see that now we are considering both states. Before I told you about U2 and UL. And then we can see here U2 does not change. Let me say this line absolutely. But we will change this. I1, excuse me, I don't remember. Yeah, I1. U2 and I1, the states, exactly the states. We can see that we have 1, 0 because the state vector is I1, U2. Of course, here 0 because when we are considering just the state or the states, we don't have, we have a D equals 0, the component of D, the corresponding component of D equals 0. What is the difference as before? The difference that here I would like to control the states, the energy, let me say the total energy. But of course, as before was no, excuse me, before was U2 and UL. No? Now here is not clear, but it's U2. Let me, excuse me, UL. Excuse me. I made mistakes because here it was unclear, U2. Here, if I want to control UL and I1, UL does not change. Before, I don't remember. Let me see because I'm trying to remember, but I don't remember what I told you. Okay. Before was U2 and UL, therefore 0, 1, and 0 here. This line here at UL, 0 minus 1, 1. Now, if I want to control UL and I1, this line, the element of the matrix, let me say C, M, and D, does not change. No? We can say 0, 1, and 1. Excuse me, 0 minus 1. Excuse me again. Excuse me, a little bit tired. 0 minus 1. 1 does not change. But of course, now it's in the first line, on the first position, let me say, because I changed the order. The order sometimes, but not necessarily, indicates priority, but not necessarily. The priority we will realize with the control. You look here. Here we have already seen. I don't need to comment. I forgot that I had it. And the other exercise that we have seen last time, the mechanical system is given the dynamical equations. Again, the matrix A and B does not change depending of the choice of the outputs, of the choice of priority, everything. Because the matrix A, B states the structural connections of the state, of the energy, cannot change. But of course, the output is our choice, depending what we want to do. Exercise, think a few seconds if I will put in the project. Please draw the block diagram. This is the block diagram. You remember, we have seen last time. I will tell you now quickly about the block diagram, which is another language to represent the system. It's the language of Simulink. last time I introduced Simile a little bit. This is the language of Simile, not only Simile. Look here. Why, in this case, the block diagram looks like something like that. And we will see now exactly the connections between these elements, which is just a translation of this language here. Is in a language is useful in particular in some tools. Simulink is one of them, but it's not the unique one. Let me show you how I can build this. This is a classical question in the project, in the examination, in our. Look, typically, but it's not a unique way, we start from, let me say, from the output. Which outputs we have here? The outputs of the equations are always the state, I1 and U2. The output of the dynamics, let me say, as the states, I1 and U2. Just in second, just in second, I come back. Yeah. Yeah, excuse me. Somebody rings on the door. 1 second. Okay. Now let me explain. You can consider I1 and U2 as the output of the state equations. Yeah. And typically we start from the output, one of them, for instance, U2. We can see between, as last time, U2 and the derivative, we have an integral. You remember last time I told you a lot, no? The initial conditions of U2 at time 0, a time when we start with the simulation or with the control. But this is clear. Do you remember last time I insisted? Now, if you look at the equation, at this equation here, which characterizes basically the dynamics of U2, we can see that 1 divided C and multiply this expression here. This means if I put here 1 divided C, and I can image here exactly this signal I1 minus U2 divided R, this is exactly the derivative of U2. We can see here, U2 derivative is 1 divided C multiply this signal here, the difference between I1 and U2 divided R. This means the block 1 divided C, excuse me, before the derivative is clear, no? Because the integral of the derivative plus the initial condition is U2. Represents, this element here, represent I1 minus U2 divided R. In accordance of this, read basically the equation. Something like this equation is represented with another language in this structure. Why? This element here is I1, we will see where this comes from, minus UR divided 2, but U2 divided R, because U2 I can take from here. 1 divided R is my constant, which I can consider multiply by U2, and I can realize the first equation, which consists in one loop, or at least explicitly in this loop here. Of course, I1 must be calculated, must be explicitly expressed, calculated. If you think the simulation can be, say, also calculated. How I can express I1? From here. But if you look at the first equation, it's easy to perform the rest, because I1, between I1 and the derivative again is before we have an integral, and you have to consider the initial condition. If I divide it by 1 divided L, again is before, as last time. you have this expression in our case, 1 divided L multiply this is exactly the derivative. This means this signal here reflects U1 minus U2. U1 is our input, which is the output of the controller. We will see a little bit today what the controller can do for us. This signal here, which must be U2, because here we have a I1 minus U2 in accordance with the structural equation. This cannot be changed. U2 came from the loop, which we already realized, which we already performed. I think, in accordance with what I told you last time, in accordance what I quickly repeated for this new system, I think to build a block diagram of a system, I think we don't have any problem. I don't know if I have to repeat a little bit, but last time I insisted a lot. No? If you look at the videos too, you can realize that it's relatively intuitive. No? Fix the concept that this language here is equivalent to this language here. I have to reflect the signals, symbolically, of course, through this scheme. Probably, again, very important, this signal here, which is U1 minus U2, divided L, because this block here means that the signal here is multiplied by 1 divided L. Reflect exactly this expression. But U1 is an external input. This means I can put here generically U1, because we will see that the U1 is the output of the controller. U2 is something which comes from the previous block or block diagram. Here, let me see. We have just a few considerations. Yeah, this is the consideration of the linearity. Just to conclude a little bit, do you remember last time I told you if I have an element which is not linear, the friction, for instance, here we don't have example at this moment. This representation is not valid. Here I put it just again the definition of the linearity and so on. No? I don't want to insist on this. If you want, you can reconsider your lecture in math. And here is not new for us. Again, the system. And yeah, again, A and B does not change. Once the system is given, the dynamics is the structural way, is the behavior of the system. Here is the output, in this case, the two states. Probably I didn't check, I didn't propose until now the two states, I1 and U2. No? Remember what UL and I1, UL and U2 and vice versa. I made mistakes at the beginning, but this is clear. I1 and U2, in this case, is the identity matrix, the matrix CM00D, because we don't need any D when we have the state, because the state is direct the energy somehow, no? But the problem which I have before, do you remember U2 and UL, we have also here, because with one input, it's difficult to control two outputs, because the two outputs are interconnected. No? In any case, when you have one input, it's just difficult to control two outputs. Therefore, this problem of the priority is there. Before going ahead with, again, I don't find here. Before going ahead with the control, let me Uh, right. For you, a model, I can write here, over interconnected um, mechanical electrical system. Let me write here. I don't know if I have already prepared. We can speed up a little bit. Let me see. Let me see. But it doesn't matter. Let me, I don't find now quickly. Mhm. Let me show you quickly a model of an electrical motor. I don't know, probably you already seen in electrotechnic, something like that. Let me see U of T in some literature we are just considering this possible graphical representation to indicate an electrical motor. Let me consider DC motor. We don't have time, of course, to analyze detail, synchron, asynchron doesn't make sense in the course of selected topic and control for robotics and automation, but just in the chapter, in the part of the modeling, makes sense. Nevertheless, this is an actuator for a robot. It's very often a DC drive motor with different variation in the structure of its design and so on. I mean, rotors, permanent magnets, number of permanent magnets, structure, and so on. How is modeled here? Yes, as I told you, the system here is in the mix between mechanical and electrical dynamics. Let me write this sentence. Mix is not a good word, but in a combination. Is in a combination of mechanical, let me write. Yeah, let me write quickly the equation. Typically, I don't know if you remember, here we have a voltage. Let me say UL. UL is strange, even though sometimes it's is UL. Let me say UL. Induced voltage. No? Induced voltage. The reaction, you remember, the reaction on the movement of the rotor is a voltage which try to limit the current E. Which states we have here? Electrical states are the current, because of the electromagnetic energy which you have in the coil. We haven't seen until now in the inductance. Then we have the mechanical states. Which one? Position and velocity. Let me write phi of t, angular position, and angular velocity. The angular velocity is clear because we have the kinetic energy. Now we are moving. Yeah, this picture recall us this concept here. Recall us this concept here. But of course, also the position is in a state because the position is the integral by velocity. We will see a little bit later, but we have already seen in this example of the mechanical system how the position is always an integral of the velocity. And the integral, we will see, that indicates the state. Because as you remember one sentence of last time, the states are variable which store energy. Which store energy. To be in one position, another position, means a difference of energy. Remember the concept of the difference of energy and so on. To move one position or another, we need energy. No? Again, on the topology, L, the inductance, represent also somehow the inductance if any, we have inductances, coils in the motor. Everything is localized, localized is a good word, better to say concentrated in one point, this means without dimension, which characterize the inductance of the system. The same for the resistance. The resistance is characterized is there because we have a coils. The coils is really realized by conductors and so on. Let me see the equations. Input is U. I told you, but I didn't write. U. Could be also the current, of course could be. Probably you are better than me in this electrotechnic aspects. If I have the current as an input, this means I need here transistors and so on, which generate the input as a current. But let me remain the classical form, U of t as the input. First equation. The first equation is basically this equation here, but you have to consider UL. This means I can write this equation here in the form of the current now, the T equals 1 divided L. Do you remember this form here in which I put in evidence, let me say, the derivative? Minus UL, this balance here. But UL is not a state. You remember, here must appear state and input. UL is not a state. We will see what UL is as a function of state. The rest is easy. And we have a similar time, this mechanical equation, which basically reflects this. Of course, we don't have the mass, but something related to the mass, the inertia, because here we don't have a linear movement, but a rotational movement. The inertia, we multiply, in our case, the force, the moment, the torque input. We will see what the torque is as a function of the states, because also this is not exactly our input. Minus, you remember this, K omega, in our case we have Kf, the friction, multiply omega t, if I am considering just and a linear friction. Of course, we can also consider here the torque as an load. Of course, the initial condition, if you like, if you don't put it, MATLAB put alone 0, 0. Now, the open question is what is UL as a function of the state? What is M as a function of the state? Let me write here. We have a constant, typically, that characterizes the motor or such kind of motor. Let me say K motor, which multiply omega t. Omega is the function of t. This is the induced voltage, typically, for such kind of motors. What about m of t? We can see that now the function of a state. Basically, running faster and faster, we have a stronger reaction. Probably you know, no? M of t is the same Km, very important, this part here, is the same, at least for such kind of, for a DC motor, which multiply the current. The resulting motoric moment, or the torque, resulting from ut, the input in voltage, which generated current, I of t, and then thanks to the structure of the motor, depends of is Km, both that's the same, that's the same, which generates the reaction, but in the meantime generate the motoric torque. Depends on how number of poles, if this is realized with permanent magnet, this number of permanent magnet structure, and so on. Now we can see the interconnection, electrical, mechanical, but you can see M of t depends on the current, which is an electrical state. UL, this element here, depends on omega, which is in a kinematic state. I, the current here, which is involved in the mechanical system, is an electrical state. Omega, which is involved in the electrical dynamics, is the mechanical state. We can see the interconnection, clearly a dynamics interconnection between electrical and mechanical states. Here, we have a mechanical states in the electrical dynamics. Here we have an electrical states in the mechanical dynamics. When we have a system which consists of both, so for instance, electromechanical elements or parts. Okay. Just to complete what I told you until now. Now we will start with the control, which you have in the slide which I said. Typically, I will redo the copy of all material in one file, and I will upload in Wacom. Let me restart. Let me restart from the system which I considered before, the electrical system. But we can also consider another system. No, it does not matter. It does not matter because for us, when we have the matrices or the structure of the equations, in case of nonlinear, the control basically consider the physical systems. Again, we can also consider this. We can put in the matrices, and I can do the same consideration for this system here. And now I'm considering a small system in order to be to do very quickly in order to proceed without many calculations. But for the concept, doesn't matter if I'm working with the matrix of matrix 2 times 2 or 3 times 3 and so on. Let me again reconsider this electrical system. Now, I would like to start introducing one control strategy which allows to define, to understand what a controller is. Look at this expression here. Definition of our controller. Definition. What is the meaning of this approach? The meaning is I can define a controller basically as I want, but please keep in mind that the controller is always as a function of the states, or at least one state. Let me say in general states. We will see why the general is more effective exactly today. And an input which we are considering our goal. We can see that we have these two elements here. We have the states, x states, or the state vector, and r of t, which our reference, which is our goal, reference goal for us, their synonymy. Yeah. Let me now go in depth mathematically. And in our case, in a parameter. Why that? Because the idea is to control just one variable, no? Because with two variables or the two states to be controlled, the control is more complicated. I don't have time here to do really this advanced structure. Very often, as in this case, if the number of input is less than the number of the controlled output, yeah, we have to put some priority. We cannot control both perfectly. Do you remember I told you before, because of interconnections. This really is a more complicated issue, even though, of course, we can understand that we have to find a compromise. Look here, now. N is one parameter to be designed. K, in our case, is a matrix, the raw matrix, which consists of two parameters. Of course, if I want to control the DC drive, which I introduced before, in this case, I have a row with three parameters, K11, K12, K13. Therefore, I told you, let me remain with a system with two variables, because conceptually it's the same, but we can proceed without many calculations. About R of t, the reference I already told you. Again, a controller is a dynamic structure, could be also not dynamic, as in this case. But in general, is a function. Now we can see U1 of t is the output of the controller. This is the controller. U1 of t equals blah, 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 blah. It's an equation. Could be in a dynamic equation and a differential equation. Could be in a static equation like this. But it's an equation in which the output of the controller, I1, is the input of the system. And the output, the controller, dynamic or static, with differential or not differential equation, is the function of the states, or the state vector, and a goal, the reference, the signal. Now, the design for this kind of actuator, controller, typically is realized in two steps. We can see that here it seems to be that we have a feedback action because X is the state of the system. This means the first step is to calculate K11 and K12, we can see that K11 and K12 will multiply our statics. This is written depending of some specifications. We will see together. We will see together. And the second step is to design n, to calculate n, in order to obtain our goal. This is in general. We can see that we have two signals, x u1 tilde and u1 hat, which came from these two separate steps. I didn't write step one and step two. I can do that if you want. But anyway, two forms of action, the sets. We can see two forms of action. Probably this wording, I'm sure came from a book. But if you want, you can say also step one and step two. Okay, basically what is written here, somehow I already explained, but let me read this for you again. Even though this is more related, yeah, what I am doing, relating what I'm doing now. Let me read nevertheless. I think it's worthwhile probably to comment a little bit. Let me consider now the static action in order to control the velocity of the changes. Yeah. And then I try to clarify before reading. Why these two steps? Because this first step, let me say, this is state action. This is state action. It seems to be clear that I act on the energy because I try, let me say, to manipulate the energy because I1 and U2 reflect the energy. Do you remember? This means U1 tilde acts directly on the energy. This means acting on the energy this action acts on the velocity of, let me say, of the changes of the states, of the whole states. This sense, conceptually, we have really two different actions. This change structurally the behavior because try to take into consideration the states. And the feed-forward action is there to obtain the goal, to be precise on our goal. But how rapid is this changes or the control system is due to K11 and K12 because this is strictly related to the state. Yeah, because I can control the dynamics of the system. This means I can control how fast change the energy inside the system, exactly what I am telling you now. No? But I cannot control directly on our possible goals, as I told you before. Because this depends, I have to fix a goal. This means I have to fix R of t. Yeah, look at this. Again, the first step or the first part of the control. This is our general system in which instead of U1, we have a U1 tilde. This means the first part of the control, our first step. U tilde is minus K of X of t. I didn't consider here and multiply R of t. Because you remember, I split U1 of t in U1 tilde plus U1 hat. Now, plugging in, I will have this. Clear? If I plug in this here, I will have this, because instead of 1 tilde, I will put minus k x of t. Sometimes students ask me, why minus? It's just a convention. It's just a convention. We obtain this. And then, no? If you put in evidence on the right x of t. AC equal exactly A minus BK is the new matrix, or the new transition matrix, if you want to be precise in the nomenclature. Last time I told you about that. Of the controlled system, the system which is already controlled somehow. At least, let me say, considering the states. And AC states the dynamics, the new dynamics, if you want, the control dynamics, no, of the system. More in depth, more in depth. This sentence here is extremely important now for us. What is the meaning? What is the meaning to control the energy? What is the meaning to control the changes? Probably you remember in math. You remember in math. When we have a matrix, when we have a linear system, we can associate to the matrix eigenvalues. The eigenvalues characterize the answer of the system, because you remember exponential function up to minus the eigenvalues multiply t states how fast change the variables, the state variables. This means the idea of this part of the controller to place, I underline this word, arbitrarily the eigenvalue of the matrix A, or the better to say, to place arbitrarily of the matrix AC. Here is not exactly precise what I am telling you, but it's clear what I intend. Which I change basically the dynamics of the original system, which is characterized by the matrix A. But of course, I cannot change, in the sense, the eigenvalue of A, but I can change the eigenvalue of AC, which starts, which is based on the matrix A, because the matrix A represents the system. Probably it is better to show the exercise than to explain this concept. But anyway, this sentence says exactly what I am telling you, because if I change the lambda is the eigenvalue, I will change the speed of the system, I will change the reaction of the system. How I can obtain my goal in terms of time, how fast, or how slow I can obtain the goal. Okay. Let me go ahead. I need a little bit time to reorganize the material, because if I use this material, I already lost a couple of slides. This is the problem. Okay, let me at least put this inside. Just to recall what I intend with eigenvalue of a matrix M. M is the matrix. I don't know if you remember this equation here. I don't have time to demonstrate the validity of this equation. But in any case, using this condition, I can calculate the value, the eigenvalue of the matrix M. I don't have time to demonstrate, or to tell you about this condition here, but I will calculate for you. In our case, I can show you in our case how I can use this condition. If on a given matrix M, I can calculate its eigenvalue using this identity. Now, in our case, we have a problem which is quite similar, but not exactly the same, because we have a matrix AC which is the controlled matrix, which is expressed in this form. Do you remember? A minus B multiplied K. Let me come back in order to show you what I intend. A minus B multiplied K. AC is equal A minus B multiplied K. In our case, K is K11, K12, to remember. K11, K12. K is K11, K12. B is 1 divided L, 0. We have seen today, no? 1 divided L, 0. This means AC formally consists of this structure. Very interesting, because AC is not in a given matrix. It's in a parameterized matrix using K11, K12. This means AC is the function of two parameters, K11 and K12. Here I didn't tell you, but I assumed that you know this equation here. I is the identity matrix, lambda is the eigenvalues. Now, the problem is not to calculate the eigenvalues M with this equation here, but the problem is to calculate K11 and K12 for two given eigenvalues, or let me say to formulate two new given eigenvalues. Because I want to state, I want to fix, I want to choose how fast or how slow is the system. I can, typically we try to speed up the dynamics, but it could happen that I need to slow down the dynamics. Typically, we try to avoid oscillations in the dynamic, but it could be that we need oscillations. This means the idea is to fix the dynamics of a new system. Let me try to do the example so we can understand better than in theoretically. This column multiply this row, we will obtain this clearly. I don't know if you remember the product between matrices or vectors, column vector and row vector. Doing this easy calculation, this 2 times 2 matrix minus this 2 times 2 matrix, I will obtain this. And then I do the same, I apply the same criterion between this matrix and this matrix, I will obtain this. This element minus this element, we have this. I think about the calculation of matrices, I don't have to explain. No? I think so that you know probably better than me. No? So here, no? To obtain this 0 minus K11 divided L is minus K11 divided L. Anyway, when we are able to obtain this expression here, I have to just calculate the determinant. This multiply this minus this multiply this. I have this expression here. Characteristic polynomial. But we can see that the characteristic polynomial here depends on K11, depends on K12, but depends also on lambda. It's quite abstract. But lambda I can fix because I would like to have in a particular controlled system. This means, look at this final expression. What we have here, I fixed one eigenvalues, and I have this equation here. Lambda 1 is given, I don't know, minus 100. Huh? Now we will see how I can choose these values. But in any case, it's fixed. And if fixed, I will fix also the second eigenvalues. This means having a system in which the unique unknown are K11 and K12. It's solvable, no? At least from the system theory, it's solvable if the system is controllable. I don't have time really to tell you about the controllability in details, but the meaning is if you have interconnections between the two dynamics, let me say so, we can place the eigenvalues as I want, and this means exist to values, to real values, K11 and K12, which allows to solve this problem here, which allows to place the eigenvalues. Now, a couple of consideration here again. How I can choose lambda 1 and lambda 2. For instance, I don't know if you remember in math. If the eigenvalues are real, we don't have oscillations. This means I can put just real values. To obtain stability, we need lambda 1 and lambda 2 with real part negative. Imaginary part, let me put to 0, because assuming that I don't want to have oscillations in the final dynamics. Final dynamic means in the control dynamics. I will put here minus 100, and the first one, the second, I don't know, minus 110. No oscillations. Now the question is, why minus 100? What is the meaning of this minus 100? Yeah, larger and larger value in absolute value, but in any case negative, because otherwise, if you remember in math, we don't have the stability. We have a faster and faster system. Now, the dynamics is a little bit complex because the dynamics depends of both lambda 1, lambda 2, but typically we can approximate, I don't know if you remember the concept of dominant eigenvalues. I don't know if I wrote here something. No, I didn't write, but I have it later something, but I anticipate. Basically, we can roughly consider the smallest eigenvalues in absolute value. I mean, if I have 100, minus 100 and minus 110, minus 100 is the dominant one. So approximatively, because this corresponds, if you think the meaning of the lambda, no? Exponential function at lambda t, lambda is negative. No? Exponential function up to lambda 1t plus, we have a constant which multiplies the exponential function, but in any case, exponential function up to lambda 2t. What is the dominant one? The dominant one is the exponential function which has the lambda smallest in absolute value. Because if the exponent is large in absolute value, this exponential will extinguish very fast. I show you what I intend here after this explanation. 1 second. Let me take something to write. And then, of course, this could be and nevertheless a possible criterion to choose the eigenvalue. Let me show you. Roughly, I have an y of t, the function of a1 exponential function up to lambda 1 t, lambda 1 with the negative real part, più plus a2 exponential function lambda 2. Now, if lambda 1 absolute value larger than lambda 2, I don't remember what I told before, but let me consider this. We can say, of course, much larger to be more precise, in order to understand the concept. We can say that y of t is, let me say, to be precise, large enough. Infinite is clear. Let's say for t large enough, that's y of t is a2 exponent lambda 2 of t. I don't know if you remember this, because this part here will extinguish faster. We say that lambda 2 is the dominating eigenvalues or the dominating exponent in this sense. Exponent lambda 2 is an eigenvalue, no? I don't know if you remember in math. And tau is, to be precise, let me write lambda 1 and lambda 2 real, no? Because it's the case which I am considering. Dominant time constant. No? Now, with the time constant, we can choose approximatively the dynamics, because you remember, typically we are considering 5 times time constant, 7 times time constant in order to achieve our goal. No? With the concept. We can choose the value of lambda 2. Of course, we have also lambda 1. No? Theoretically, we have to consider also this one, but approximatively, and then with the computer, we can adjust the value. You remember this constant here. 5 times or 7 times tau is the steady state dynamic. Dynamics. The reason is after 5 tau, or the 5 times the dominant time constant, we achieve the goal. In order to understand how I can choose lambda 1 and lambda 2. Lambda 1 must be larger, no? Theoretically much larger. Otherwise, of course, we have an influence, but in any case, this criterion could be used. We will see in MATLAB, we don't need to do a big effort because we have a function place which allows to solve this for given lambda 1 and lambda 2. I will show you. Now we take a rest a little bit. Let me tell you about but I will tell you later. I will tell you later about this n. My idea is we take a rest a little bit, we relax a little bit later with MATLAB, and then I will tell you about the calculation of n. Yeah, I would like to take a rest now. We will see in 15 minutes as before, and then we will go ahead until 15 past 5. Not today, if you have time for me. No, of course, if you have time. Let me nevertheless, yeah. What about n? We will see after the simulation. Let me remain here. I have already prepared simulation, I hope, so we can proceed a little bit faster. We will see here let me say 40, yeah, in 50 minutes. Let me now Okay, now in this part, we go in depth on the design of the matrix K, this raw matrix, in order to explain a little bit better, I hope, with the help of the Kalman, with the help of the simulation, how this matrix K changes the dynamics, change the, we can speed up, we can slow down, change in any case the dynamics. Because again, theoretically, the matrix K uh, realize the feedback, the energetical feedback, because K considers or takes into consideration the states. K1 multiply I1 plus K12 multiply U2. This is the controller at the end, or the part of the controller dedicated to the dynamics. Let me share now the MATLAB. I will send you, not only I will upload in Wake if one of you can help me later at the end of the lecture. I would like also fix up. Look here. This is an M file. About the M file I told you last time, no? A little bit, I hope. We have an RL circuit. It's used here, the M file as net data file. Clear, close, clear means clear everything which we have active in the kernel of MATLAB. Basically, we can see here on the right part the workspace, to be precise. No, in the workspace at this moment we don't have anything, but clear allows to cancel variables which can be present in the workspace. It's just a prophylax action. It's not a functional action. Close the window of the figures and so on. Then I put here the data: 1 ohm R, inductance 10 up to minus 4 Henry. This way to write is the particular MATLAB form. No? This means E, or the A up to minus 4 is 10 up to minus 4. No? This means 10 up to minus 4. Do you remember I told you last time this semicolon is just there to avoid that these values appear in the workspace, excuse me, in the command window. In the command window when I run the software. If I don't put this, it's not a big problem, because I will see here in the command window the values. Then again, I put the matrix A, B, C, M, and D in accordance with what I told you now until now. No? Here it seems to be that I want to monitor I1 and U2. Do you remember this was the last representation which I proposed? 1001, this identity matrix means that I will look at the variables, the state variables. We don't need, in this case, don't need in the sense we need just D equals 0, no information about, no zero in the component of the matrix. It's exactly what I told you at the end. I mean, A and B does not change because this is the dynamics. This is came from the physical representation. But choosing one variable, so two variables, and which variables change the output representation. This change the matrix C, M, and D. Here, again, I would like to monitor, at least with this choice here, I would like to monitor both state variables. Look here. Lambda, eigenvalue for matrix A. This means I am calculating here the eigenvalue of the system. EIG calculate directly what? You remember, determinant of lambda I minus A equals 0. Probably you remember better than me. Let me put a comment for you. But in any case, if you write help EIG, it is plain. No? But let me write. Command EIG calculate calculates the eigenvalue. To be precise, the right eigenvalue, but forget it. No, we have a right and left eigenvalues, but forget it. So then, look, I will perform. I will create a vector P with two components, 10 times real of lambda 1, 20 times real of lambda 1, with the new desired eigenvalues. Why that? Let me read the comment and then I will explain the common place. When I perform this vector P, it seems that at least we can see here, at least 10 times the dynamics of the original system should be considered time faster, in the sense, should be considered for the new control system. Why that? Because P is the argument number 3 of the common place. Place is a function of MATLAB, which consists of 3 arguments, which works with 3 arguments. First argument is the matrix A, second argument is the matrix B, second argument is the matrix P or the vector P, in which in P I will put the new eigenvalue, the eigenvalue of the controlled system, basically of the matrix AC. Let me come back to the lecture in order to clarify this, and then I will open also the help. What place does? Place. Hmm? Place is a function with 3 arguments. Why that? Because he needs information A, he needs information B, he needs the 2 eigenvalues, lambda 1 and lambda 2, to calculate k11, k12. What place does solve these algebraic equations in terms of k11 and k12? Let me come back to MATLAB and let me show you very shortly the help. So you learned, probably you know already MATLAB, but anyway, if you write here help EIG, for each function of MATLAB, you can use the help in order to understand what I'm doing and so on. Look, eigenvalue of A produced in a column vector uh, containing the eigenvalue of the square matrix A. Now let me see help place. Look, we have 3 arguments, as I told you. A is the matrix A, B is the matrix B is the matrix of the input of the system. P is the vector of the new eigenvalue. This is specified. Uh, Let me enlarge a little bit until here. Basically, as I told you, compute the matrix K, in our case K11 and K12, such that, again, this expression which I already told you during the lecture, A minus KB, KA, BK, A minus BK, minus plus in the convention. But MATLAB uses this convention, in which P is the vector of the specified eigenvalues. Mm. Let me come back here. I calculate k. We will see in a few minutes how I can calculate n. Let me open Simulink. Let me run this one. As a result, here we have a k. Two values for k in accordance with our specification. Typically, it is written in my comment as that the lambda is the desired lambda must be real, no? But it's not necessary because if I need oscillations for some reasons, very often I don't need oscillations. But if I need oscillation, the eigenvalue must be complex. Let me see the eigenvalue for A. Yeah, we can see the eigenvalue of A, they are complex. The matrix A, we have oscillation in the matrix in the original system. We have oscillation. We can see from here, no? The imaginary part is not zero. This means in our case, we will obtain results without oscillations because I'm considering just the real part. Hmm? I don't know if I forgot to analyze this. Very often is so, but not necessarily. Sometimes the oscillation is also something which we want to have. No? Typically, we try to avoid. Let me open MATLAB. Let me show you the simulation. I hope the file will work. Let me see if, yeah, almost ready. Let me try to share. There's some problem here. Let me share now. Look. It's not, this is just the model. This is just the model. We can see that reflects the block diagrams. Let me see if I find the controlled system. Um, Strange. Okay, let me open another. What is this one? Okay. This means we can build together. Let me run the simulation. I'm running. Yeah, we can see exactly uh, our block diagram. Look at home a little bit, but it's exactly our block diagram realized with Simulink. Here's an equivalent. The equivalent model realized using the matrix ABCD in MATLAB. Let me see if No, excuse me. Yeah. No? Yeah, there's not so much to see. Let me, because the system is quite fast. Let me show you. Just in a comparison, in order to show you that we can realize the system using the block diagrams, but also this block here is the way. Yeah, if I share, we can see that the representation is the same. Probably you have seen in some different courses this. We cannot distinguish between yellow and blue line because the representation used the blocks is equivalent with the representation using the compact form ABCD. This is the goal of the simulation. Now, let me try to let me try to control the system. Okay, let me come back here. Hmm. Let me short the simulation time. Ah, stupid. Let me write 0, 1. Let me start. Hmm. This is the little bit results. No? Hmm. Let me now apply the controller. Let me apply the controller. Yeah. How I can apply the controller? I need to consider the sum. Let me consider now the same input, but of course, n, this parameter, is 1 in our case, is not designed. Let me put here inside plus plus. And now, let me consider the matrix K from the state I1, U2 to the feedback here. Yeah, this means I go here inside. Let me share in order to understand. Better. Not element-wise, but matrix. Do you remember? K multiply U. U is our vector I1, U2. K is our matrix. Calculated offline by my program, my function place. No? Let me share again because the system mm. This is the result. We can see that in 0,02, or let me say 0,03, we achieve this goal, a goal, without thinking about which kind of goal. But in any case, we obtain this 0,03 with oscillations. Let me share. We obtain the goal. It doesn't matter which kind of goal. 0 at 0,0, let me say 3. Look what happens now. Running the simulation, considering the controlled, I don't know if I click, probably not, now, The control, mistakes. Let me see which kind of mistake. Probably I forgot to say something. Let me see. Yeah, I see the error. 1 second. Yeah, 1 second. I try to correct. Yeah, no. Um, Probably is K. Let me see. K. We go MATLAB. Okay. Okay, I will correct here. No, it's correct. Okay. I forgot. I show you what is there. I forgot to write here K. The gain is the matrix K. I have a problem with Simulink. Zoom. Now, K, the product between K multiply I1 U2, because the vector U is exactly what I told you now. Let me repeat again, if now we have errors. This is the results which we have for in a given goal. It doesn't matter which one. 0,03, more or less. Let me see what happens with the controlled. I forgot minus. Excuse me again. Was minus K. Do you remember? Was minus K. Let me write minus K. I didn't share, but believe me, do you remember I put K? But I told you many times that we need minus K. Let me see. You can see that a goal, it doesn't matter which one, that we will fix. We will achieve much faster. Theoretically, 10 times, or more or less 10 times faster. Why I'm saying more or less? Because we have an exponential function. This means it's not 10 times, it's not exactly 10 times. But you can see here, more or less 0,03. Because of course, the beginning, let me say so, an exponential function can be approximated in a line. Now we can see that the advantage, no oscillations, if no, the oscillations are not desired, it's faster, 10 times faster than the original one, at least, of course, approximatively. I told you many times what is the meaning of this approximation. Because we have two time constants, not one, but in general, we can design very well. Let me come back to the lecture and let me conclude with N, and then I show you N. Let me. What about N? Now, to simplify, to conclude quickly, let me consider that I want to control the voltage of the capacitor U2 at a constant value. What happens if it's not constant? We will see a little bit next week. We will see a little bit next week. But let me introduce this concept of the parameter and using, I need a very few minutes, using U2 and a constant. Look, in any case, as I told you, the goal must be known. I mean, this constant must be known. Exactly. If you look here, U2 isn't a constant, which in any case must be known. And looking now at the second equation, as is written here very quickly, let me show you this concept here. The second equation is basically written here again. If U2 is known as is a constant, assume it is a constant. I called here, I changed the name, constant one, but so you can consider constant is not so. I don't remember why I changed in constant one. Yeah, because now we have a constant two, which is basically here. Let me see how I can justify. Let me take this another slides. Yeah, considering now. Excuse me, this made mistakes. This is the equation one. Excuse me. This is the equation one. Let me read again. If U2 is a constant one, from equation two, we have this also I1 is a constant, which I called constant 2, therefore I changed the name, equals, or the better to say, I1 equals constant 1 divided R. This means the constant 2 is constant 1 divided R. How I can demonstrate this? It's easy. Because if you look at the equation number 2, is here. The second line. I don't know if it's visible, in which U2 is a constant 1. Let me show you directly this probably is better, even though I have to consider that if U2 is constant 1, the derivative of U2 with respect to the time is 0. Therefore, I will end up in this equation. I don't know if this is visible. The second equation here, the second line, let me say, is this multiplied this minus this multiplied this equals 0. So this is 0, and this part here, it's 0. I don't know if you remember, I showed you these two zeros. This means in the second line, we don't add anything. Consider this part here. I don't know if it's visible, this equation here, from this line here. The second line, let me say. 0 because the derivative of U2 is in a constant with respect to time is 0. This multiplied this, I1 divided C minus 1 divided RC multiply U2. And this contribution is 0. This in any case is 0 because this row with this, this column with this row, if this is 0, we have a matrix which is K1 1 divided L, and then K1 2 divided L, and then 0 0 in the second line. This means this equation can be really justified by this product. And at the end, we have that I1 is U2 divided L, because C I can cancel with C. Or, if you like, constant 1 divided R. No? Or, this element here is also in a constant 2. Meaning of this. Now, from the first equation, if I plug in I1, which is here, in the first equation, believe me, you can verify at home in any case, that you have this expression, which we can see that is our I1. Is this enough to plug in I1 here? as constant 1 divided r, or if you want, constant 2. And we can see that will appear k11, k12, but it's easy to show you. Because here, the derivative I1 with respect to time is 0. Now, if you solve this equation, considering, for instance, as r of t is a constant 1, but not necessary. We will see also next week with this remark more in detail. But why not? I can put whatever I want. But constant 1 is more suitable because it's exactly in the next I will show you if it's not the case. Nevertheless, we will concede, we will obtain the goal. But anyway, if R1, our goal is constant 1, because our goal is constant 1, U2. U2 is our goal, constant 1. This means R of t could be considered constant 1. If it's not, we will see that it works nevertheless. Yeah, we can see you can choose R of t equals the general constant in this case. But of course, the suitable choice is exactly R of t is equal constant 1. But anyway, we will see next week. Let me show you if the goal is constant 1, R of t, I told you at the beginning, is our goal. I put here constant 1. I can cancel constant 1 everywhere if this is constant 1, and I will obtain my parameter n. Believe me, no, it's enough to, this is a gymnasium example, no? From high school. N from this can be calculated. Constant 1 I can cancel. I will have, thus n is equal at the end, this expression. We can see that depends of k11 and k12, also from on R in our case. Let me quickly, give me a couple minutes to implement. We already have this. Here, I tried also to verify some robustness. We will see next week. This is the exact expression. But of course, if I don't know exactly R, for instance, we have some problems. But let me, at this moment, calculate analytically. I have n. Let me now implement this n here. This means I need to put n here. Why it doesn't work? Yeah. And then you will see that I will obtain my goal. Which goal? This here. 12. This is our R of t. And this is a constant. We will see next time if I don't put constant 1, but no reason. Don't put a constant 1. Constant 1 is our goal. 12. If our goal is 12, we will see now what happens. This means I am concluding. I am concluding U2, which is this one, should be 12. Let me see. In 0,03, if I remember well, 0,003, no? Because we speed up 10 times. Yeah. Of course, what is the limit of this approach? I'm concluding. The limit of this approach, I already told you, that if I don't know some parameters, for instance, R, we will see next week, we have and a bias. Because n depends on the knowledge of the parameters. For instance, R, but not all. If you want, I can, 1 second, I can show you what I intend. Let me change. Look, here, for instance, not only R, here I changed a value of K12, because K12, I didn't tell you exactly, but depends on the parameters, R and L, because was R and L was inside. Now I change a lot, no, in order to show you. Was inside in a system, which one? This here, let me show you. Which depends on the parameter L, R, and C. This means if I don't know exactly L, R, and C, I cannot calculate exactly K11 and K12. Now I put an exaggeration in order to show you let me show you what I intend. Here's an exaggeration. We can see a 5 times in order to show you on K12. But also interesting, you remember before we had this 10%. If I don't know R directly, look what happens. I'm really concluding. Next week we will go in depth on this. This was the simulation. Let me simulate again with just an error in R. You can see that we don't have exactly 12, something less. To conclude, really now, this approach is easy, relatively easy, but not robust, we say, not robust, with respect to the knowledge of the parameter. But sometimes, nevertheless, can be used. Nevertheless, can be used. Depends the level of knowledge which we have of the system, depends of the level of precision which we want to obtain. Okay, now we will conclude here for today. We will see next week. I hope to be more without delay. We start without delay. If one student of you can help me a little bit in Wake Camp, I try to organize a little bit the material officially, even though at this moment I think you have almost everything. I will scan uh, for Wake Camp, and in any case, also the simulation will send you these 2 files, or I will upload in Wake Camp. At this moment, let me close the lecture, and then we will discuss about the material. Thank you for your attention, really, for attending this lecture.